Okay, so today we're going to talk about quantifiers, which is section 2.4 in your textbook. But in order to talk about some more specific things about quantifiers, I first want to do just a brief detour on just a couple of definitions from section 5.1, which is set operations, which hopefully are not totally new to you. So it's not going to be so crazy to do this out of order. Okay, so given some sets, I just want to define some operations on sets. So we're going to talk about 5 operations. So suppose that A and B are some sets, and let's fix some universal set U. Okay, so I'll explain in a second why we need to do this, but maybe the U is a set of all real numbers, and we're picking some sets A and B of real numbers. Okay, here are the 4 set operations. So the union of A and B is defined as follows. So it's A union B. And the definition in set builder notation is a set of all x's in the universal set such that x is in A or x is in B. Okay, so as usual, the LaTeX for this symbol is \cup. It comes up like a cup. And so given 2 sets, basically the union is just you throw everything that's in A and everything that's in B into the set. That's the union. So we could draw a picture of this. The usual way to do this with a Venn diagram, right? So if this is A and if this is B, this big box is the big universal set U, then the union is everything that's in A or in B or both, right? Because or in math is inclusive or usually. Okay, maybe let's move this off to the side a little bit. So the intersection is the next one of A and B is A intersect B. This is of all x's in U such that x is in A and x is in B. Okay, the LaTeX for this is \cap. So the intersection is all of those elements that are in both A and in B at the same time. And so I guess here the blue is A union B. The intersection is everything that's in both A and B at the same time, so just the middle bit. And so the middle bit is A intersect B. Okay, the next set operation is called the difference. So the difference of A and B. So here we'll take A minus B. This is a set of all x's in U such that x is in A and x is not in B. It's everything that's in A, but also not in B. So it's like you're subtracting B off of A. You're taking A and you're subtracting off in some way all the stuff that's in B. So this symbol is \set minus. This is like the set theoretic difference. Okay, so maybe I'll draw a new picture here. Hopefully, I hope you can guess what this picture is. So I'll use a different color. So everything that's in A but not in B is all of this stuff, right? So this is A minus B. And finally, the complement. The complement of A is A complement. It's a set of all x's in U such that x is not in A. Okay, so this is just a superscript C that I'm using. What does this look like? I guess the last picture here. So this is just in relation to one set, right? So The complement is just everything that's not in the set. So this blue here is A complement. Okay, and so this is why we need a universal set in this definition, because again, the complement is everything that's not an A, but you need to know what everything means, right? So if you change the universal set, then the complement would be different. Right? So like, for example, if U is the integers, right, and A is the even integers, then A complement, that's all the integers that aren't even, that's the odd integers. Right, but if here U is the real numbers or something, then A complement is just all real numbers except without the integers in them, without the even integers in them. So this is like the set of all X and R such that X is not an even integer. Right, so my point is that this set and this set are different because the universal sets are different. So if there's going to be some ambiguity, then you need to specify what the universal set is before you talk about complements. Otherwise, no one will know what you're talking about. Okay, so the reason that I wanted to bring up these set operations is because we can talk about how different open sentences that we can form out of other open sentences, we can talk about their truth sets. That was really complicated the way that I just said it, so let me do it via example. Okay, so let's let U be the universal set for a variable U. Sorry, for a variable X. And let's suppose that P of X and Q of X are open sentences, so in the same variable. And P of X has truth set A, and Q of X has truth set B. Right, so P of X and Q of X involve the variable X, and all of the values of X that make P true, that's some set A. All the values that make Q true, that's some set B. We can talk about some statements built out of these, right? So for example, we could talk about the statement P of X or Q of X. And then we can ask, okay, well, what is the truth set of this new open sentence? Right, so this is a new open sentence built out of the two open sentences P of X and Q of X. Right, so maybe we can say something like, just as an example, let's think about maybe P of X is like the statement X is odd. That's a nice open sentence. Q of X is like the sentence X is prime. That seems reasonable enough, right? So this new open sentence is X is odd or X is prime, P of X or Q of X. And we can ask, what is the truth set of this thing? Right now, these sentences that I've written have kind of obvious truth sets. Let's say U is the integers. I should have said that, right? The truth set for X is just the set of all odd integers. And the truth set for Q is the set of all prime integers. Right, okay, so if I'm going to talk about integers, maybe actually it's better to talk about n, because then we won't worry about whether the negative number should count as primes or not. Well, what is the truth set for this new open sentence, P of X or Q of X? X is odd or X is prime. Maybe I should say here, A is the odd integers, B is the prime integers, odd natural numbers, prime natural numbers. Well, P of x or Q of x, what values of x to make that true? Well, it's any values of x that make P true or make Q true, which means anything in A or anything in B. So this open sentence has truth set A union B. Okay, so maybe what I'll ask you to do is figure out which statements have truth sets corresponding to the other operations. So which statements have truth sets like this? Okay, so I guess I should tell you to pause your video and do this, but hopefully you did it. And hopefully you got that the statement P of x and Q of x has truth set the intersection, because P of x and Q of x is true if P of x is true and Q of x is true, which means that something in its truth set needs to be both in the truth set for P and in the truth set for Q, which means it needs to be in both A and B at the same time, which means it needs to be in the intersection. For A set minus B, hopefully you wrote down this. This is at least one way to do it. P of x and not Q of x, because in order for this statement to be true, x needs to make P true, so it needs to be in the truth set for for P. And it needs to make not Q of x true, which means that it needs to not be in the truth set for Q. So it needs to be in A and not in B, which is exactly the difference. And then A complement is the truth set for not P of x. Okay, so one reason that I want to talk about set operations now, in addition to the fact that it's sort of a basic thing to do with sets, is because we can now apply this idea to truth sets. Okay, but I guess I didn't really give any specific examples for these operations. I just drew the pictures. So I'm going to do an example that I stole from my friend, who's another postdoc in the department, Dr. Geckner. And back in 2018, or maybe it was 2019, I was covering a class for him. And it was this class, it was Math 300. And he had this example that I just thought was so pretentious that I loved it. So in seeing what this example is, you'll get a really good idea for what kind of person my friend, Dr. Geckner, is. Maybe not the kind of person you want to be friends with. Sorry, Bennett. So what we're going to do is we're going to let our universal set here be the set of all people who have ever lived, let's say. And we're going to let A be the set defined as the set of all x and u, such that x is a composer. And we'll let B be the set of all x and u, such that x is French. Okay, so for example, e.g., like Bach is in A, right? Because Bach is a person who's lived who is a composer. And maybe one of my favorite people, Joan of Arc, is in B. And now the pretentious part of this is, let's try to figure out A union B, A intersect B, and A set minus B. And it's really funny to ask this to a class, and some people have no idea what to say. It's not that easy to think of these sets. Okay, so what is A union B? This is the set of all x such that x is a composer. So the set of all people x or x is French. And now this is much more fun if I ask you to shout out some things that are in the set, but you can't. So some people who are composers or French, so like Joan of Arc is in here because she was French. Bach was in here because he was a composer. Maybe Napoleon, composer, maybe Mozart, right? Beethoven. So the union is you just throw everything from A and everything from B into one set. So this is this set will consist of all people who are French or composers. So there will be like millions of people, hundreds of millions of people in this set. Okay, now, again, the funny part is when I say, okay, well, what does an A intersect be? So this is a set of all X such that X is a composer and X is French. And I'm pretty sure that Bennett, my friend, Dr. Geckner, wrote this example just to show off his knowledge of composers because he's a real classical music buff. But I guess it's less funny when it's a pre-recorded virtual lecture. So I guess I'll just fill in some. You should try to think of some composers. So there's Debussy, there's Ravel, there's Camille Saint-Saëns, Georges Bizet, right? He wrote Carmen, but he was French. Satie. I'm sure you thought of hundreds of others. And then, okay, in my notes, I have, it doesn't really matter how I do this, but B minus A. What is this set? This is a set of all people X, such that X is French, but X is not a composer. It's fun either way. Now you can just name some French people, right? So, I don't know, Charles de Gaulle. I guess we still have Napoleon from up there. Louis XIV. Right? I don't know if you're into sports, Thierry Henry, or maybe Tony Parker. Okay. To be honest, kind of a gratuitous example, but it's more fun in person. Okay, but you know, that's enough on this diversion. I want to go back to quantifiers. So quantifiers finally. Okay, so let me recall once more something that we've talked about several times, which is that 3x plus 12 is less than 2 is not a statement. I've said this like 100 times now in this class, but it is an open sentence. But there's a different sentence, which is there exists a real number x such that 3x plus 12 is less than 2. And this is a statement, right? You can say that this is definitely true because you could take x to be negative 100, right? So this is a statement. Okay, and the reason why this is a statement is because we don't have a variable x sitting around that's just sitting there as a variable, right? In the first sentence, 3x plus 12 is less than 2, x is just a variable, right? So as you plug in different values of x, it is true or it's false, depending on what x's you plug in. But now the statement contains this phrase, there exists a real number x such that 3x plus 12 is less than 2. So this sentence, or this clause, this quantifies the variable x. It tells you what you mean by x. And so that makes the whole sentence a statement. And so this is the first example of a quantifier. This is our first quantifier. There are two quantifiers that we need to worry about. Okay, so here's the definition. Man, these notes, I really should do these quantifiers in the other order. Let me do this quantifier in this order. Okay, so the phrase there exists, or its equivalents. So there's more than one way to say it in English, but or like you say, there is a real number x such that 3x plus 12 is less than 2. That's saying the same thing as there exists a real number x such that 3x plus 12 is less than 2. But this phrase is called an existential quantifier. Existential. Because what it does is it asserts the existence of such an x. Okay, so this quantifies the variable x by saying there exists some x. Okay, so there's a symbol that we use for this in shorthand, and it's a backwards E. E for exists is used as shorthand to denote the existential quantifier. Okay, and so this symbol is backslash exists in LaTeX. So we already have an example of this, right? There exists a real number x such that 3x plus 12 is less than 2. Here's another example. There exists a real number x such that x squared equals 2. This is a statement, right? And it's a true statement. Why is it a true statement? It's a true statement because there does exist a real number x such that x squared equals 2. Right? There's actually more than one. There's two of them. But the point is that this is true because this open sentence has a non-empty truth set. Right? Because there is something that makes the open sentence true. So we'll say that the existentially quantified statement is true if some element of the universal statement makes the predicate true, if the quantified statement has a non-empty truth set. So the existential is true. So I'll write it like this. There exists x such that p of x is true if the truth set of p is not empty. Okay, so let me talk about the shorthand for a second. Okay, the shorthand is just shorthand. It means that if you're writing a formal proof in your homework or an exam, then the formal proof needs to be written in words. If you go look at inside of a textbook, inside of a math paper, if someone wants to say there exists something, they say the word, they write out the words there exists. On the other hand, it's a really useful shorthand because you can write it extremely quickly, which means that if you're thinking about something, it's much easier to write, or if you're taking notes or something, it's much easier to write this. Let's even do it like this. There exists an x in R such that x squared equals 2. This is how you might write symbolically. This is just shorthand though. Okay, so if you go to like a math professor's blackboard someday when the school opens up again and we're seeing each other in person, you'll see the symbol written on people's blackboards because they're writing notes to themselves. But if you see the paper that they write afterward, they will write out the word there exists whenever they need it. Okay, so it's a useful symbol to know, especially if you're taking notes in class or something. But I caution you that you will want to use it too much. So it shouldn't appear in formal writing. Okay, and the last note, this is just something to know for yourself, is that oftentimes if you see this exists with an exclamation point, this oftentimes means there exists a unique. Right, so for example, I could say there exists a unique natural number x such that x squared equals 4 because there's only one natural number. It's 2, positive 2. Okay, so I don't know how often I'll use it in this class, but it's a very common shorthand, so I thought that you should know it. Okay. Our second quantifier is called the universal quantifier. Okay, so the phrase for every or its equivalents is called a universal quantifier. Okay, and the symbol that we use is an upside down A. Okay, and the LaTeX is / for all, because for all is another way to say for every. Okay, let me give you some examples, right? So you could say for all real numbers x, x squared is greater than or equal to 0. That is a statement, right? Because you know whether it's true or false. It's not an open sentence because we've quantified the variable x using the universal quantifier. So here's the quantifier. This quantifies x. And so this statement is true. Why is it true? The reason that this statement is true is because this open sentence is true for every x, right? For every real number x, x squared is greater than or equal to 0 is true. In other words, the truth statement for that open sentence is every element of the universal set. No matter which real number x you pick, it's true that x squared is greater than or equal to 0. So this is true because x squared is greater than or equal to 0 has truth set R. Right, so let me write this in notation like this. So for all x, p of x is true if the truth set for this predicate, for this open sentence p of x, is all of u. And that's really what you mean. If you say for every real number x, x squared is greater than or equal to 0, when you say that, what you mean is the truth set for x squared is greater than or equal to 0 is every real number. Okay, and again, there are many ways to say either of these things in English. In fact, I think I've said several of these already. So for all real numbers x, or for every real number x, or given any real number x, x squared is greater than or equal to 0, are all ways to say the same sentence. Right? So for every real number x, x squared is greater than or equal to 0, or given any real number x, x squared is greater than or equal to 0, or for all x in R, x squared is greater than or equal to 0. These are all examples of the same quantified sentence. Right? These are all the same. In shorthand, you would say for all x in R, x squared is greater than or equal to 0. But again, this one is shorthand. So I want you to be comfortable with it. And okay, so I said something like you probably shouldn't use that on an exam. On an exam, I probably wouldn't be too harsh because you have a limited amount of time. But on our homework sets, if you're writing a formal proof, I don't want you to use these symbols because the symbols don't belong in a formal proof. Okay. So we can also have statements that involve more than one quantifier. Okay, so statements with more than one quantifier. So let's see if you can write this statement. Okay, so let's call this an example. I want you to write the statement in symbols, just so that you should be able to practice going back and forth. I'll have some homework questions where you have to go back and forth. So for all natural numbers x, there exists a natural number y such that x is less than y. Okay, so write that in symbols and then write this statement in English. I'll give you a different statement. And then I'll ask you to pause the video and do it. Here's a statement. Exists y and n for all x and n, x is less than y. Okay. So hopefully you paused the video and did this. So this first statement is for all natural numbers x. So for all x and n, there exists a natural number y. So there exists a natural number y such that x is less than y. That's this first statement. Maybe I should have done it in a different color. Okay, what is the second statement? There exists a natural number y such that for all natural numbers x, x is less than y. Okay, notice that we put in phrases like such that, so that what we're reading makes sense as an English statement. And where you put them in matters, right? In order to make a grammatically correct English sentence. So here we put a such that here right before the x is less than y, but here the such that really belonged here. And it's just because of how it reads as an English sentence. So the first one is for all natural numbers x, there exists a y such that x is less than y. The second one says there exists a natural number y such that for all natural numbers x, x is less than y. Okay, and one question is, are these the same thing? Another way of asking this question is, does the order of the quantifiers matter, right? Because the only difference between these two statements is just in one statement, we put the for all first, and in the other statement, we put the there exists first. So e.g. or i.e., does the order matter? And the answer to this question is these are not the same. Whoops. And the order of quantifiers does matter. Okay, why? I claim that one of these statements is true, and the other one is false. Is that true? No, neither of these statements is true. Neither of these statements is true. Okay, but what does the first statement say? The first statement says, for every natural number, you can find, oh wait, sorry, the first one is true. For every natural number, you can find a natural number that's bigger than it. For every x, there exists a y such that x is less than y. So in the first statement, it's like you're picking the x first. No matter which natural number you pick, I can find a bigger natural number. Right, so this one is true because, for example, if you give me an x, for any x, there does exist a natural number bigger than it, like x plus 1 is a natural number that's bigger than it. So that first statement is true. On the other hand, the second statement is false. There exists a natural number y such that for all natural numbers x, x is less than y. What is this thing saying? This is saying that there exists a natural number that's bigger than every other natural number. There exists a y. There's a single natural number y that's such that no matter which natural number x you give me, y is going to be bigger than x. And this is not true. This is false. There is no natural number that's larger than all others. So since the first statement is true and the second statement is false, these statements clearly can't mean the same thing. Okay, so the order in which you quantify your variables matters. In the first one, it's like, pick any x you want, I will find a y. So it's like the x came first, and then I get to pick the y that's bigger. In the second statement, it's like, oh, I'm going to pick a y. There is a y, a single y, that's bigger than every x. The order in which you do these things matters. Okay, so order matters. And there will be lots and lots and lots of times in mathematics where you will quantify several variables, and the order in which you quantify them changes the sentence completely. Okay, and then the last thing for today is I would like to talk about negating quantifiers. So let's talk about how to negate a quantifier. So let's consider the sentence, the true sentence. It's not a true sentence. Everybody loves math. Okay, one way that we could talk about the sentence is we could write it symbolically. So we could let U be the set of all people. And then this statement becomes, for every x in U, for all x in U, x loves math. This is one way to write everybody loves math. Okay, well, how do you negate this statement? How do you negate the statement everybody loves math? Okay, well, a tempting but incorrect answer is everybody does not love math. So incorrect negation is everybody does not love math. Which in symbols would be for every x in U, x does not love math. But this is incorrect because this is way too strong to be the negation. Right? How could the first statement, everybody loves math, be false? In order for that to be false, and it is false, there just needs to be somebody who doesn't love math. We don't need everybody to not love math for the first statement to be false. We only need one person to not love math, and the first statement is false. Whereas this red statement that I've written, everybody does not love math, is way too strong. It says that everybody doesn't love math. So how do you negate everybody loves math? The true negation is there exists some person who does not love math. There exists some person who does not love math. That's how you would negate the first statement. So you would say there exists an x in U such that x does not love math. So the point I'm trying to make here is that if you negate a universally quantified statement, what you get is you get an existentially quantified statement of the negation of the open sentence. So what do I mean by this? So that is to negate. So if you take the statement for all x in U, P of x, the negation of this is there exists an x in U such that not P of x. This is how you negate this universally quantified statement. Okay, also, we could talk about the statement, at least one person loves math. The statement is true because you love math. Okay, so in symbols, I could say there exists an x in U such that x loves math. How would you negate this? How can you negate at least one person loves math? Well, the negation is everybody does not love math. That's how that could be false. How could it be false that at least one person loves math? Well, nobody loves math. Everybody does not love math. So the negation of their let's say the negation of this is for every x in U, x does not love math. And so to negate the existentially quantified statement, there exists an x in U such that P of x, it's for every x in U, not P of x. Okay, so when you negate a statement, you have to sort of flip the quantifier and negate the sentence, the open sentence. Okay, so the last thing I want to talk about is how to negate a quantifier or a statement that has multiple quantifiers in it. Right, so let's talk about the following statement. Oops, let's put this in black. Let's negate for all real numbers x, there exists a real number y such that x is greater than y. Okay, so we can think about what this statement means. We can try to negate it based on what it means. But one really nice tool that we have is we can sort of write this in symbols to write it in a more compact notation, and then think carefully about how to negate it, and then at the end see if it makes sense. So what is the statement really saying? It's saying for every real number x, you can find a real number that's smaller than it. Right? For every real number x you choose, there is a different real number y, such that y is smaller than x, or x is bigger than y, which seems true, I guess. How could that statement be false? It would be false if there was some real number where you couldn't find one that was smaller than it, right? But that's maybe a little bit hard to, you have to think hard about that. So let's use our tool of let's write this statement in terms of symbols, and then think about how to negate the whole thing in terms of symbols. It's sort of a tool that we have. Okay, so if I want to write this in terms of symbols, I can say for all x in R, there exists a y in R such that x is greater than y. Okay, and again, the nice thing about these symbols is that it allows us to really compactly write down the thoughts that we're thinking. And I want to negate this thing. This is what I'm after, right? This is what I want. Well, I can view this as a universally quantified statement. For all x in R, the thing in the red parentheses holds. And we know how to negate a universally quantified statement. What you do is you flip it to an existential, and then you negate the part that comes after it. So to negate this, I could write this as there exists an x in R such that not there exists a y in R such that x is greater than y. Right, because that's how you negate a universally quantified statement. But now here what I have is I have the negation of an existentially quantified statement. I sometimes say qualified when I mean quantified. The negation of an existentially quantified statement. And we know how to negate an existentially quantified statement. You flip it to a universal, and then you negate everything that comes after it. So this should be equivalent to there exists an x in R such that for all y in R, and then the negation of x is greater than y. This is just using the things on the last two slides. But then we said that you should always try to write the most natural negation of a statement. And the most natural negation of x is less than y is probably, x is greater than y is x is less than or equal to y. So I would say that a nice negation of this is there exists a real number x or an x and r, such that for all real numbers y, x is less than or equal to y. And let's see if this agrees with our intuition for how to negate the statement, right? So the statement, again, said no matter which real number you pick, you can always find a real number smaller than it. How could that be false? That would be false if there was some real number that had no numbers smaller than it. And that's exactly what our last statement is saying. There exists a real number x such that every other real number y is bigger than or equal to x. In other words, x has no real numbers that are smaller than it. So this process that we did with the just sort of symbolic manipulation yielded a correct negation. Okay, so if you ever have a complicated sentence that you need to negate, you just sort of take it piece by piece, one at a time, you're able to negate the whole thing. Okay, so that takes us to the end of chapter 2. The next lecture will begin 3.1, which is on direct proofs.